And here in example 4, they want us to find the upper and lower sums of a region. Find the upper and lower sums for the region bounded by the graph of f of x is x squared, and the x-axis between the numbers 0 and 2. So here is x is 0, x is 2, and we're looking at the area under this parabolic curve. F of x equals x squared. And first we'll look at the inscribed rectangles. We go up, we hit the curve, and we're going to go over to the right, so this is going to be an underestimate. The first thing we should figure out is what is our delta x, or our dx? How much is our x value changing? And remember that was b minus a divided by n. And they're not telling us to divide it up into any given number of rectangles. We're going to sort of do this abstractly. So our upper limit is 2, our lower limit is 0, all over n. So that is 2 over n. The width of each rectangle is 2 over n. Okay, and sometimes coming up with these, the formulas for the left and right endpoints are the hardest part. So our left endpoints, or we're using lowercase m sub I. And remember for here, since we're under this curve and it's a parabola going up, our first endpoint is right at the origin, is at 0. So we're going to start at 0, and we want to add something to it, but we want to add something that's really not going to move us anywhere, because we do want our first left endpoint to be right at the origin. So, this is our first interval. What if we add to it I minus 1? So for our first interval, we'll have 1 minus 1, which is 0, and then we got to have in there also the width of the rectangle, so to speak, 2 over n. So our first left endpoint will be 0 plus, 1 minus 1 is 0, times anything is still 0, so that will be 0, our first left endpoint. And I wonder, should we do the right endpoints now? No, we'll do the right endpoints when we get to the overestimate there. And let's see if we try to get this all as one fraction. I want to clean this up a little bit. Let's see. Yeah, if we just multiply, that is I minus 1 over 1. If we multiply straight across, we're going to get 2 times the quantity I minus 1 all over n. So there is our left endpoint formula. So S lowercase, S sub n, our area, our lower sum underneath the curve, is going to be the summation from I equals 1 to n, whatever n value we choose, of f of lowercase m sub I times the width of the rectangle delta x. So when we plug in what we found up here, we're going to have our S of n is the sum from I equals 1 to n, f of this. And remember, this is the squaring function. So we're going to take what we found for our left endpoint, 2 times I minus 1 all over n. That's quantity squared. So that's the height of the rectangle, and then the width of the rectangle is 2 over n. Now remember, any numbers that we can and any n values we can pull out front and put them here in front of the summation symbol. So let's see what we can accomplish with that. We're going to have our summation from I equals 1 to n. Let's see here. If we distribute this 2, we're squaring this quantity, so this is going to be a 2 squared quantity I minus 1 squared and an n squared down in the bottom. So we sort of distributed that out. So if we look across the top, all our numerators, what can we factor out? Well, 2 times 2 is 4, times 2 is 8. We can pull an 8 in the numerator out. And that just leaves us I minus 1 quantity squared. What can we pull out in the denominator? Well, anything that's an n we can pull out. N squared times n is n to the third. So we've factored out 8 over n to the third. And now we have I minus 1 quantity squared. And I guess we can get rid of some of this. So if we FOIL that out, we'll be able to plug in some of our formulas. So we're going to have our 8 over n to the third, our summation from I equals 1 to n, and if we FOIL this out, we'll get I squared minus 2i plus 1. And we can break that into 3 separate summations. Let me even get the picture out of here for a little more room. Oops. So let's break that into 3 different summations. We're going to have 8 over n to the third, and we're going to distribute that across all the summations. So we're going to have our summation, and I'll stop with the upper and lower notation. We'll have our I squared minus, and we can factor the 2 out front, 2 times the summation of I plus the summation of 1. And now it looks a little more agreeable. We can go back and plug in some of the formulas that we had earlier in the video and start to work this out. So again, our 8 over n to the third is out front. That will be distributed across everything. I squared. We can replace I squared with n times n plus 1 times 2n plus 1 all over 6 minus we're going to have 2 times the summation of I. So that was n times n plus 1 over 2. N times the quantity n plus 1 over 2. And then remember, this summation was from I equals 1 to n. 1 times n is n. And we're done. And let's see here, these 2's will cancel. And then what we got to do is sort of FOIL this all out and clean this all up. You could do that on the TI-89. That's going to be 8 over n to the third. And when we FOIL this out, collect our like terms, we're going to be left with, let's see here. Excuse me, that's not going to be 8 over n to the third. Again, when we do get everything in order, we're going to have 4 over 3n to the third. And then when we condense all this down, we're going to have 2 n to the third minus 3n squared plus n. So what we did, just distributed all of that, factored out what we could, reduced the fraction, and got everything in the parenthesis, all our like terms collected. Now if we go back and distribute this, we're going to get, what's that going to be, 8n to the third over 3n to the third minus, 4 times 3 is 12n squared over 3n to the third plus 4n over 3n to the third. And we are going to have some stuff cancel. The n to the thirds are gone. So we have 8 thirds minus. That's going to be divide out to a 4, and the n squared takes out 2 of these, so 4 over n plus 4 thirds can't reduce, but the n up top wipes out 1 in the bottom, and that'll get knocked down to an n squared. So this is our lower sum. For any value of n that we choose. Now let's talk about the upper sum, or the right endpoints here. Again, sometimes the hardest part is coming up with that little formula to get these right endpoints. Again, we want our first endpoint to be here. It's going to be away from the origin. So capital M sub I for the right endpoints, or the upper sum. We are going to start at the origin, and we're going to add something to it. I times 2 over n. And let's see if that works out. We plug in our first rectangle. We plug in our first one, so that would be 1 times 2 over n, or 2n. And that's the width of a rectangle, like we figured out at the beginning when we did b minus a divided by n. That was the width of a rectangle, and that is the width of this rectangle. That'll be our right endpoint. And if we just clean that up a little bit, we can multiply I times 2, and that's over n. So that's going to be 2i over n. 2i over n is our right endpoints. So when we do the summation here, let me get this picture out of the way. Remember, we use a capital S for our upper sum. Capital S of n is going to be the summation from I equals 1 to n of f of capital M sub I. We're just running, our endpoints through our function times delta x, the width of each rectangle. And in this part of the problem, that's our summation from I equals 1 to n. Remember, it is just a squaring function. Our function is just x squared. So we're going to take that 2i over n, and square it, and multiply that by delta x. The width of the rectangle is 2 over n. So let's see what we got here. Our summation from 1 to n, that's going to be 4i squared. So 4i squared over n squared times 2 over n. So let's get all our n's and stuff and numbers separate from the i's. Oops. So we still have our summation. I equals 1 to n. See, we have a denominator, n times n squared is n to the third. In our numerator, we have a 4 times 2, that's 8. And then we have our I squared. So, this 8 and n to the third, those are just numbers. Those can come out front. 8 n to the third. And we can replace I squared. We know what the formula for the squared was. That is n times the quantity n plus 1 times the quantity 2n plus 1, all divided by 6. Okay, if we drag the 6 out here, that's going to be 8/6, which reduces to 4/3 n to the third. Oop, that n to the third is in the denominator, n to the third. And then if we FOIL this out and collect up our like terms, we're going to have 2n to the third plus 3n squared plus n. And just like we did in the last example, if we distribute through, we're going to have 8n to the third over 3n to the third plus 12n squared over 3n to the third plus 4n over 3n to the third. And just like last time, we're going to have some stuff cancel. So let's see here. The n to the thirds are gone. We're left with 8/3 plus 4 over, and then our n squared is going to wipe out 2 of these, just a plain old n in the bottom, plus here 4/3, the fraction will not change, but our n in the numerator wipes out 1 in the denominator, and we have an n squared. So this is our upper sum. Looks a lot like the lower sum. If we flip back and forth, we have 8/3 starts both of our sums. And then in the upper sum, it's plus 4 over n and minus 4 over n in the lower sum. And then we have our plus 4 over 3n squared in both of them. So in example 4, it illustrates some important things about lower and upper sums. First, notice that for any values of n, the lower sum is less than or equal to the upper sum. This sum is going to be less than the upper sum, because that's a minus and that's a plus. Second, the difference between the two sums lessens as n increases. As we subdivide our area into more and more rectangles, the difference between our over and under estimate gets less and less. In fact, if you take the limits as n approaches infinity, the more rectangles the better. Well, how about infinitely many rectangles of infinitely thin width? Both the upper and the lower sums are going to approach the same limit, 8/3. So we apply this idea of a limit. As n goes to infinity of this, the 8/3 stays. But as this denominator goes to infinity, this term goes to 0. 3 over 3 times infinity squared divided into 4 is 0. So we're just left with 8/3 for the lower sum. If we apply the same limit idea to the upper sum, we have the same 8/3 at the front, and then 4 divided by infinity is 0. 4 divided by 3 times infinity squared is 0. Our upper sum is also 8/3. The next theorem shows that the equivalence of the limits as n approaches infinity of the upper and lower sums is not a mere coincidence. It's true for all functions that are continuous and non-negative on a closed interval from a to b. The proof of this theorem is best left to a course in advanced calculus. So here's our theorem 4.3. Limits of upper and lower sums. Let f be continuous and non-negative on the interval from a to b. The limit as n approaches infinity of both the lower and upper sums exist and are equal to each other. That is, here it all is in our limit notation. As n approaches infinity, we have our lower limit and our upper limit, and those two are equal. Where delta x is b minus a divided by n. That's just, we're dividing our interval from our upper to our lower limit into n subdivisions. And f of m sub I and f of capital M sub I are the minimum and maximum values of the function on the interval. Because the same limit is attained for both the minimum value and the maximum value, it follows from the squeeze theorem that the choice of x in the ith subinterval does not affect the limit. This means that you are free to choose an arbitrary x value in the ith subinterval, as in the following definition of the area of a region in the plane. So let f be continuous and non-negative across the interval from a to b. The area of the region bounded by the graph of the function, the x-axis, and the vertical lines x is a and x is b is the area is equal to the limit as n approaches infinity of the summation from I to n of our function f of c sub I times delta x, where delta x is equal to b minus a divided by n. See the figure. Here's our curve. We want the width of the ith subinterval here. Delta x is x sub I minus x of sub I minus 1. And we have our rectangles are going to be the height, f of c sub I. Whatever f value we plug into the function will give us the height at that point. In example 5, we're going to find the area by this limit definition. Find the area of the region bounded by the graph f of x is x to the third, the x-axis, and the vertical lines x is 0 and x is 1. So here in the picture, we're going from 0 to 1 on the x-axis. Our function is the cubic function. We're going to divide that into infinitely many subintervals and find the area that exists underneath that curve. So, what is the width of each rectangle? Remember, that is b minus a divided by n. And let's see, our b value, our upper limit is 1, our lower limit is 0, so 1 minus 0 is 1 over n. That is the width of each of our rectangles. And this area, the area, using our limit definition, our limit notation, is going to be the limit as that value of n approaches infinity of f of c sub I times delta x, where this is just the height of the rectangle. We're plugging our endpoint into the function. That's going to be the height of the rectangle, and this is the width of the rectangle. So let's plug in what we have for our problem. Our limit as n goes to infinity. Oh, and I forgot the summation notation here. That is the limit as n approaches infinity of the summation of I equals 1 to n of our function. So our limit n goes to infinity. Our sum is from the first interval to the nth. And remember, our function is the cube function, x to the third. So we're going to have I over n to the third times I over n. Oop, that's an I. Where again, this is the height of the rectangle given to us by the function, and the 1 over n is the width of the function. So We're still thinking about this as a limit as our n goes to infinity. Let's see what we can pull out front here. We're going to have an I to the third. Oh, this is not an I, that is a 1. 1 over n is the width of our rectangles. I'm sorry, that's 1 over n, not an I. So, I to the third is going to be up top, and n to the third in the denominator, and we have another n here. So that's an n to the fourth. We can sort of pull out a 1 over n to the fourth. So we've distributed this third power, and we've multiplied our n times n to the third. So now all we're left with is the summation from I equals 1 to n of I to the third power. And that's something we do have a formula for. So that third power, we still have this, again, we're still thinking as a limit as our number n approaches infinity. We have our 1 over n to the fourth, and the third power, I to the third power, we can replace with n squared times the quantity n plus 1 squared, and that was all over 4. So right here on this diagonal, we can see a little cancellation will go on. We have an n squared and an n to the fourth. N squared is completely wiped out. This n to the fourth will be now reduced down to an n squared. And if we FOIL out what we have here in the parentheses, let's see, we're going to have a 1 over n squared. And I guess we could have pulled the 4 out there with it too, huh, in the bottom. Pull that denominator 4 out, and then we have this quantity, n plus 1 squared. So that's n squared plus 2n plus 1. And now when we distribute this back through, our 1 in the numerator won't change anything, but every one of these will get a denominator of 4n squared. So we're going to have a 4n squared, another 4n squared, and another 4n squared. And now we let, we're still thinking about this as a limit as n goes to infinity. Well, now we can apply that limit. Oh, I dropped my n there. So let that limit go to infinity. We've distributed that throughout. So the n squareds are going to cancel. We're going to be left with a fourth plus. The 2 and 4 will reduce, and the n in the numerator will wipe out 1 in the denominator. So we're going to have a 1 over 2n plus 1 over 4n squared. So as the limit, as n goes to infinity, we're left with a fourth plus, this term will be 1 divided by 2 times infinity, which is 0. And 1 divided by 4 times infinity squared is 0. So it looks like we have an area under that curve of 1/4, whatever the units were, squared. Units squared. Okay, in example 6 here, there's a little twist. We're not going right from an x value of 0. We want to find the area of the region bounded by the graph of a downward opening parabola, 4 minus x squared, the x-axis, and now the vertical lines are x is 1 and x is 2. So here in the picture, we only want this light pink shaded area. There's our parabolic curve, and our values from x is 1 to x is 2. We want our subintervals to be underneath the curve and between 1 and 2. So what is our delta x? What is the width of each rectangle? Well, it's just going to be 1 divided by n. Remember, it's b minus a divided by n. B is 2, a is 1, so 2 minus 1 is 1 divided by n. So there's the width of each rectangle. And for this one, we can use right endpoints. Again, sometimes this is the hardest part to figure out. Because we're not starting right at the 0, our beginning is going to be at 1. So it's going to be our right endpoint, a, or our left endpoint, excuse me, a plus something delta x. and that's just going to be I delta x. So we want our first well, let's even skip that. And our A, our left point here is our 1, because we're not starting again at the origin. 1 plus I times delta x. Well, I, and our delta x we found above is 1 over n. So it's going to be I times 1 over n, or 1 plus I over n. Let me get the picture out of the way so I have a little more room here. So our area, A, is going to be our limit as n approaches infinity of our summation from I equals 1 to n of our function f of, our c sub 1, or c sub I, times delta x, the width of the rectangle. The f of c sub I is the height of the rectangle, delta x is the width of the rectangle. Oops. So we have our function, so we can plug in something for this. Our area is going to be the limit as n goes to infinity of our summation from I equals 1 to n. And our function is 4 minus x squared. 4 minus x squared. And we figured out our x was 1 plus I over n. 1 plus I over n quantity squared, and that is the height of the rectangle given to us by the function, and the width of the rectangle we found was 1 over n. Okay, let's see if we can make this a little easier to work with. We still have our limit as n goes to infinity. The 1 over n we can factor out front, 1 over n. And then we have our summation from I equals 1 to n. And let's see what goes on in here. We have our 4 minus, and now we can FOIL this out. This is 1 plus I over n quantity squared. Well, if we FOIL it, we're going to have 1 times 1 is 1, plus I over n plus I over n is 2I over n, plus I over n times I over n is I squared over n squared. And let's see, we have to remember to distribute our negative sign. Our limit as n goes to infinity, 1 over n, our summation, I'll stop at the lower and upper limits there. So here we're going to have 4 minus 1, which is 3, and then the negative will be distributed, minus 2I over n, minus I squared over n squared. And now we have 3 different things added or subtracted together. We can break each of those into their own separate summation. And remember, each of them will have their own 1 over n out front. I'm going to drop, no, I'll squeeze it in here real quick. The limit as n goes to infinity. So we're going to have 1 over n times the summation of 3, minus, we have our 1 over n, the summation of 2I over n. And let's see, we could factor out, we can pull the 2 out, and we can pull this denominator n out. So before we go any farther, we have our 1 over n out front. We factor out a 2, so it's going to be 2, and then n times n is n squared. And then we're just left with the summation of I. Minus, we have an n squared here, and a 1 over n is already out front of our summation symbol. So that's going to be 1 over n to the third summation. Oop, that's an ugly summation. And let me clear a little more room here. Summation of I squared. Okay, and remember, on all of these, we're summing from 1 to n, 1 to n, 1 to n. Well, let's see here now. We're Gotta remember we're still thinking about this as a limit as we're going to infinity. The summation of just a constant is the constant times, our upper bound. So that's going to be 1 over n times 3n. And the n's are going to cancel. So we're just going to be left with plain old 3 for that term. Minus, we have 2 over n squared. And let's see, the summation for just plain old I. The summation for that is n times n plus 1 over 2. So our I we replace with n times n plus 1 over 2. And we'll see here the 2's will cancel. This n will cancel with one of these. So it looks like we're going to have n plus 1 over n. So minus n plus 1 over n. And then minus, we have our last term here is 1 over n to the third. And we replace I squared. I squared we replace with n times n plus 1 times 2n plus 1. Squeeze that in there. All over 6. So let's see, this is going to be a tricky one. Our denominator is going to be 6n to the third. And the numerator, I'm going to do a little scratch work up here. Change to red. So our first two terms, if we multiply, we get n squared plus n times 2n plus 1. And if we FOIL this out, 2n times n to the second is going to be 2n to the third plus an n squared plus another 2n squared plus n times 1 is n. So we have 2n to the third plus 3n squared plus n. So 2n to the third plus 3n squared plus n. And we might as well just squeeze this in right now. This 6n to the third will be a denominator for each term. Ooh, I could have just left that there. So this has a 6n to the third denominator. This has a 6n to the third plus 6n to the third. So we're going to have our 3 minus, let's break this up into some chunks. We're going to have n divided by n plus 1 divided by n minus, here we're going to have 2 divided by 6 is a third, and the n squareds cancel. We can distribute the negative, and then the 3/6 will reduce down to a half. The n squared will wipe out 2 of these, so we're left with an n. Distribute the negative again, and we're going to be left with 1/6. The n up top wipes out one of these over n squared. And remember, we're looking at this as a limit as n goes to infinity. Well, now we can let n go to infinity. So we're going to have 3 stays the same. N divided by n, we could reduce that. That's a 1. Plus 1 divided by infinity is 0. Minus a third. Minus 1 over 2 times infinity is 0. Minus 1 over 6 times infinity squared is also 0. So we're left with 3 minus 1 minus a third. And that comes out to 5/3. So the area we were looking for under this curve, from 1 to 2, the area under the downward opening parabola 4 minus x squared, the exact area of that is exactly 5/3 units squared. This last example looks at a region that's bounded by the y-axis rather than the x-axis. So, example 7, find the area of the region bounded by the graph of f of y equals y squared. So this is a sort of sideways opening parabola. We want the area between that curve and the y-axis. and between the y values of 0 and 1, as shown in the figure. So we're just going to have a little different notation. We're sort of turning everything kind of 90 degrees. We usually want a delta x, our change in the x-axis, but now we're sort of walking along the y-axis. So we're not going to have a delta x, we're going to have a delta y. But we're still chopping it up into subintervals. That's our b minus a divided by n. You know, b is the upper bound, here it's 1, a is the lower bound, 0. So we have 1 minus 0 over n, or delta y is 1 over n. A lot like we had in another example with delta x. And our, we'll call them upper endpoints. Let's see, our first endpoint, c sub I. You know, we're starting here at the origin. You know, what's going to be our first interval, our first endpoint? Well, it's just going to be I divided by n. And our area is going to be our limit as n goes to infinity of our function f of c sub I times delta y. Again, this is the sort of the height of the rectangle, but now it's turned 90 degrees. Delta y is the width of each rectangle on the y-axis. And now, you know, this is a nice easy function to plug in there. It's just a squared function, y squared. So we're going to look at it as a limit as n goes to infinity of our function, our summation, the sum of I equals 1 to n of our function squared. I mean, this is just y squared, so that's going to be I over n quantity squared. That's the height, so to speak, of the rectangle, and this is the width, 1 over n, our delta y. So let me get a little of this out of the way. And remember, anything that is n, we can sort of drag out to the front. So we're going to have our limit as n goes to infinity. I'll leave some room here to the left of our summation from I equals 1 to n. So this is a quantity squared. If I distribute, it's going to be I squared over n squared, and then that's multiplied by 1 over n. If we multiply our denominators straight across, we'll get n to the third power, and we can drag that out front. 1 over n to the third, and then we're just left with I squared. And we've used that before. That's not going to be hard to deal with at all. So we have our limit as n goes to infinity. We have our 1 over n to the third, and we can replace I squared with n times n plus 1 quantity times 2n plus 1, all divided by 6. Let's see, to make life easier, before we distribute some stuff, we can at least cross that n off and take one of these out. So that's now an n squared. And let's see what happens. We have our 1 over n squared. And we'll work inside our parentheses here. It's all going to be over 6. And if we FOIL this out, n times 2n, 2n squared. We're going to have a plus n plus 2n's. That's going to be a plus 3n. And then 1 times 1 is 1. And of course, we're going to break this into individual fractions so we can apply that limit. Oops, didn't want to do that. So again, we're still thinking this is the limit as n goes to infinity. And let's see what happens here. We're going to have 2n squared is our numerator, 2n squared. Our denominator will be 6n squared. Plus, our numerator is 3n, we distribute our n squared in the denominator, 6n squared, plus 1 times 1 is 1, 6 times n squared is 6n squared. Here the n squareds cancel, and we have 2 6, which reduces to a third. Here this is going to reduce to a half, and our numerator n is gone. This is knocked down to an n to the first power. So we're going to have plus 1 over 2n plus 1 over 6n squared. As we apply the limit, let n go to infinity. Our 1/3 is untouched. But 1 divided by 2 times infinity is 0. 1 divided by 6 times infinity squared is also 0. So we're left with a third. Again, we were looking for the area bounded between the y-axis and our curve, and that area is exactly 1/3 square units.